I'd like to introduce our next speaker, George Kesidis from Pennsylvania State University. George is going to speak to us today about detecting adversarial examples in deep learning. George, as I mentioned, is yet another one of those folks who needs no introduction, but I will nonetheless introduce him. George is currently, as I say, at Pennsylvania State University. He has been, his work is known far and wide, has done quite a lot for DARPA, AFOSR, quite a bit of work for Cisco, and plenty of work with NSF over the years. His work spans networking and economic policy and applications of machine learning. I'm sure that this is going to be a great talk. This is one I have not heard, but I'm excited to learn more about. And as I mentioned in my introduction at the beginning, I really think that this is a third element of the pipeline where we've got users of data science, and we've got the techniques that really enable good data science. And I think that this notion of how we deal with the notions of neural network classifiers as black boxes and try and mitigate those sorts of attacks is an important element of our application of some of these new techniques. So with that, I will turn it over to George for his talk. Thank you, George. Yep, you're good now. Thank you. Yep,
okay.
You're good. Thanks.
Thank you, Sean, and thanks to the organizers for the invitation. This work is in collaboration with my colleague, David Miller, and we're going to tag team on this talk. I'm just, for the sake of time, okay, now I can't. Okay, so we'll talk a little bit about what an adversarial example is. The expression is used a little vaguely. We call them test time evasion attacks, typically in our papers. We'll briefly mention our first foray into the defense against test time evasion attacks. And then, as you know, the solution to a problem with neural networks, you have to throw another neural network at it. We'll describe recent ideas using GANs as a way of detecting TTEs. And then we'll follow up with broader discussions about robust AI and other types of adversarial learning attacks that maybe I'll skip over those because previous speakers covered that. Okay, so the idea of an adversarial example is that the example is classified to, let's call it a target or destination class, but it looks like an example from another class. Let's call it a source class. And it's difficult to detect. So if a human looked at the sample should look like a source class sample, even though the classifier is saying it's a target class sample. And the sample shouldn't otherwise look suspicious. So it should be difficult to detect. There are many different types of test time evasion attacks. You could think of a network flow as modifying how it forms packets and how it transmits them in order to evade a network-based anomaly detector. Malware engages in poly and metamorphism. Why? Well, it's in order to evade detection. And of course, techniques of camouflage are examples of what we'll call physical attacks. One can modify the sample digitally, and as a result, you're free to make all sorts of modeling. You're not constrained by any, there's no physical constraint in forming the attack. And there are papers that are written addressing both types of formulations of adversarial examples. So this is an early paper in the area that sort of kicked it off. A lot of papers in this area work on images because, I think fundamentally because of convenience. I should just make a comment. So there have been papers on adversarial AI that consider a wide variety of data domains: text, speech, imaging. And it isn't just classification. There are concerns about neural networks that are used for translation or for time series prediction or regression. And some of the more interesting examples are along those lines. But it's nice to give a talk with images because it's so visual. So here's an example of a test time evasion attack. The idea is that this is on the MNIST data set of handwritten characters, digits, I should say. The diagonal of this matrix represents unmodified images as they were handwritten. And then the off diagonal represents the attacked image. So you can see, for example, here, this is a JSMA version of a 0. That's the source class. And the classifier was deceived into classifying this as a 3. Okay, so this, for example, here, this is the unmodified 5, okay, from the source class 5. And this is what JSMA did to the 5, perturbed it in order that it's classified by the classifier by the neural network as a 2. Sorry, in this case as a 1. Okay. So what you have here is a rather weak attack. It's an example of a weak attack because it's pixelated. This is not a natural way of writing characters. So anyone looking at this would say, this still looks like a 3, sure, but someone has, or this still looks like a 5, perhaps, but someone has, pixelated it. There's salt and pepper noise, and it's actually quite easy to detect this by simply counting the number of contiguous white regions. Typically, a natural handwritten digit either has 1 or 2 contiguous white regions, and this is a good example of a 5 because it has 2 contiguous white regions. There's a gap here. Whereas when you add salt and pepper noise, you get a large number of pixelated regions, and you can base a detector on that. That's very, very accurate and has 97% ROC AUC. So how are test time evasion attacks crafted? There are some well-known ones, JSMA, which is the previous slide, FGSM, and the Carlini-Wagner attack for images are very well known and widely cited. The way they're constructed is very similar to techniques of neural network inversion from the 1990s. These 3 attacks actually, have pretty visible artifacts on MNIST. There's salt and pepper noise, as we just saw, and the other 2 will exhibit a lot of gray ghosting. And so it's quite easy to detect. They're quite weak on MNIST, but FGSM and CW attacks are quite strong on color images. So it's very difficult to see, okay, this color image is fishy when it's a well-crafted FGSM or CW attack. When you set up attack defense experiments, it's important to clarify in your experiment what does the attacker know and what does the defender know. The attack construction typically assumes access to the targeted AI or some reasonably accurate surrogate. They may also assume access to the defense. So it's often common standard that if you have a defense, that you're proposing a defense, that you assume that the attack knows about your defense, and so strengthening the attack accordingly. So this is what's called a white box attack, and we addressed white box attacks in our earlier work. So let's give an example. I hesitate to give figures like this because, in fact, in a realistic AI, the decision boundaries are extremely complicated, and of course, we're projecting very high dimensional features onto just 2D. But this kind of gets a sense of the 2 types of test time evasion attacks. So if we think of the light blue class at the top, those are training samples of the light blue class, and the darker blue or black class at the lower left are target class. And suppose I want to craft a test time evasion sample which is going to be classified to the target class, but really looks a lot like a source class sample, a light blue sample. So what do I do? In this example here, where you nudge a source sample just across the decision boundary, is sometimes called a low confidence adversarial example, or TTE. Oops, I'm sorry. So it's a small perturbation. But it is possible to add a very large perturbation in magnitude to and still create an effective TTE in some domains. So there are these 2 extreme kinds of adversarial example. So before we go on and talk about defenses or ways of detecting against them, some authors have talked about robust classifiers that try to correct classifier decisions on these perturbed examples. The problem is that some of these perturbed examples may be class ambiguous. Let me just switch back a few slides to an example. So this This 5 that's in the 5th row and in the 2nd column, this one here, we can see, well, you know, this is kind of class ambiguous. What is this thing? And so insisting that you classify this as either a 5 or a 1 or some other character, some other numeral, may not be the best idea. So secondly is that robust classifiers that effectively add perturbed examples to the training set with correct labels obviously can do that only for using known attacks. And we'll discuss this later. They may actually result in biasing the decision rules on clean samples, depending on how that's done. Operationally, it may be more important to simply detect, first detect whether a sample is suspicious, and then decide what to do about it. So, including our own, a number of earlier papers on detection had the following approach. Suppose that we have a trained neural network at the top, and the training samples from different classes. Different classes that correspond to different colors here. These training examples will activate an internal layer that's a good representation of the raw feature space for purposes of classification. So it may be the first max pooling layer in a convolutional neural network. So by modeling the internal layer activations of the neural network during training, you can formulate a null. Alternatively, and we'll talk about this more, you could employ a generative adversarial network. Now, when the AI is deployed in the field, the test sample will also stimulate that same internal layer that you formulated null. And based on the null or the GAN, you can determine whether that test sample was anomalous with respect to the training set. Okay, so this anomalousness with respect to the training set is not really an objective of classification directly. So the softmax output layer of the classifier is actually a pretty poor gauge of this kind of anomaly that we're interested in detecting test time evasions. And people have proposed that as well, using just the softmax layer. So the idea is to augment the classifier that's deployed with an anomaly detector, so that when a test sample is presented, you'd like to know, as you're classifying, whether that test sample is typical of the training set or perhaps highly atypical of the training set. Okay. So what we did is in an earlier paper, we focused on low confidence test time evasion attacks, and we formulated a special Kullback-Leibler detection criterion for them and demonstrated that it was effective. So what we're going to discuss in this talk is a GAN-based approach. And let me just make sure. I'm going to hand it off to David now. David, I know that you had difficulty connecting. Are you online?
I'm online. Can you hear me?
All right. Yeah. So so David will take the reins now, and what I'll do, I'll just simply say that the GAN-based approach addresses simultaneously both low and high confidence test time evasions. So with that, take it away, David.
Okay. Thanks. And George, if I do cut out, I sincerely apologize, and you'll take over.
Yeah. I'm sorry.
So just before I talk about GANs, just to preface, so these test time evasion attacks, there are two perspectives I'd like to give on them. One is that they are a security threat. If you have an automated vehicle and it misrecognizes some kind of road sign, of course we can have dire consequences of that. So certainly these are security threats. But in my opinion, actually, the larger implication for the existence of these test time evasion attacks is that basically what they imply is that deep learning, deep neural networks are not really quite there yet as a robust pattern recognition system comparable, say, for image domains to a human being. Because in the previous slide that showed the JSMA images, except for the ones that were highly ambiguous with, you know, really gross, hugely gross artifacts introduced by the attack, a human being can clearly recognize the source class instance from the attacked example. And so essentially the attack fools the deep neural network, but it doesn't fool human being. And to me, this is demonstrating a deficit in DNNs, in quote AIs, as robust recognizers. And so we want to augment them with a detector to improve their robustness. Okay, so we're not the first ones to propose GANs for anomaly detection, and we're not even actually the first ones to propose GANs for detecting test time evasion attacks. Some previous versions of GANs have been used, have been proposed for detecting test time evasion attacks. But the reported performance in those papers was pretty poor. The performance of the GANs anomaly detector that we will talk about here is excellent. It's really very, very strong performance in detecting these attacks. George, can we move to the next slide? So the type of GANs that we have used in our work is called in the literature ACGAN. And a GANs, first of all, just to very briefly summarize what a GANs does. Basically, a GANs is a game theoretic, involves a game theoretic learning framework. And there are two elements typically in this GANs. There's something called a discriminator and something called a generator. And the generator is a simulator. It's trying very hard to produce output that is consistent with training examples. Say, for example, training images, okay? And the discriminator is trying to distinguish, George, can you go back to the previous slide? The discriminator is trying to distinguish what the generator is producing from the training examples. And the different versions of GANs, well, the AC GANs in particular, its generator is what we'll call class specific. So the input to the generator, is a random input and of some dimensionality, and in this case a class label. And basically the class label is telling the generator, try to produce an example of, say, MNIST digit class 2. And so the generator would produce an image that is maybe a facsimile of a 2. The generator is trying to reliably assert that the generated examples are not legitimate. They're simulated. They're not.
Is that David cutting out? I guess that's David cutting out. So just to follow on real quick, I apologize for this. Can you guys hear me okay?
Yes.
Okay. The X data in this case is the training set here. So the discriminator is basically trying to discriminate between generated synthetic examples and actual training examples. ACGAN also also has a classifier inside of it, basically. So what you're seeing is a softmax output of a classifier and an anomaly detector as whether it's real or fake. What's coming out of the generator is real or fake. The basic idea is that the test time evasion example would be detected as a fake example. Okay. Sorry. These are the slightly different from a traditional GAN. The ACGAN, because it's both a class, the discriminator is both a classifier and an anomaly detector, you have to create a training objective that includes a classification task, and that's what this objective does with the discriminator. I probably, for the sake of time, don't have time to go through it. What we did that's different from prior work is we created a number of different features out of the ACGAN system. One was essentially the anomaly detection, whether the discriminator is subjected to a real or a fake, thinks it's subjected to a real or a fake example. The second is the softmax output of the discriminator. And then there's something called reconstruction loss, which is important. It's actually quite complicated to compute reconstruction loss. So the idea of reconstruction loss is that, again, what's happening operationally is you're effectively putting the test time, a test example into the discriminator to see if the discriminator thinks that it's typical or atypical of the training set. Reconstruction loss has to do with the generator. So the idea is that let's reverse engineer what the best Z could have been, approximation of the test time evasion example. So it's trying to reverse engineer the best input Z that would have created so let's just look at the criteria here. So we see if X is a test time evasion example, then what you're doing with reconstruction loss is what's the best output of the generator that would have been close to X. All right, I probably don't have time to go through this specific example, but effectively, operationally, if I can just go quickly back to this figure, operationally, what's happening is at test time, the GANs is trained while the AI is trained. Then at test time, the test example stimulates an internal layer, and that internal layer, pardon me if I go down here, is fed into the discriminator that you see here. That internal layer is fed into the discriminator, and that's what produces a real or fake and a softmax output, like basically another classifier output. And the reconstruction loss is determined by the generator that was trained when training GANs. So those are the statistics that we draw out of GANs. In the experiments that we run, I just take a little bit of time to show a typical experiment. There's somebody, that's probably David wanting to be admitted. I don't know that I can admit him. Oh, I did. Okay. All right, we use the MNIST and the CFAR10 data sets, color image data sets. We use a standard ResNet 18 neural network. For attacks, we use both high and low confidence Kerlin-Wagner attacks, FGSM attacks, all targeted. The baseline methods were, our own prior anomaly detector for low confidence TTEs and the FNet and ACGAN, the incumbent one that was using a GAN system. We used a partial AUC criterion. And so this is some of our experimental results where we have a number of different attacks that are per column. Each column represents a different type of attack. And then each row represent, the first two rows are other approaches. And then the last four rows are whether we use one statistic out of the GAN or several at the same time. This all AD, we use several at the same time. And we see that the performance of the ACGAN based system is better than the incumbent performances. Okay. David, are you back or?
I am back.
Okay.
I just don't know. I don't know if I'll kick out again.
Okay. Well, let me just continue and then maybe you can field questions toward the end. So there's another way of actually there's a way of visualizing what's going on that may be useful. So effectively, let me just jump to the figure. David, do you want to talk over the figure? You want to go ahead?
Sure. So basically, this figure is showing two-dimensional visualizations the point is when we apply our detection method, we can apply GANs to synthesize the input to synthesize images, or we can apply GANs to synthesize internal layers of the deep neural network classifier. And you can imagine if you're very close to the decision layer of the deep neural network classifier, the deep neural network classifier is being fooled by the attack. So we would expect that if we look at signals in a layer that's close to the decision layer, we would expect that there is confusion. The deep neural network exhibits confusion between attack samples and clean samples from the attack, the target class of the attack. And on the other hand, if you look at layers that are closer to the input, we would expect that there's a better chance of seeing there's a better chance that the GANs detector can distinguish attack examples from clean samples from the targeted class. And that is borne out experimentally here in these four figures. In the upper left quadrant, where the GANs is generating images, the input layer to the deep neural network. In the right quadrant, upper level, it's generating an internal layer signals in an internal layer close to the input layer. Internal layer 2 is a little further, a little deeper into the network, and the penultimate layer is very close to the output layer. And basically what we can say about this figure is, especially if you look at the penultimate layer, you can see that the attack there are some clean samples from the targeted class 1, the green class, that fall into the distribution of the attack samples. And so this is showing you that if you look at this layer that's close to the decision layer, it's hard to distinguish attack samples from clean samples from the targeted class. And if you look at the other three figures, the attack samples are all disjoint, well separated from the clean samples from, in fact, both classes. And so any of the other layers are suitable for use within our detection scheme. So in our detection scheme, you have to pick a layer that you're going to generate, either the images themselves or an internal layer. And we can see that layers close to the input layer are more suitable than closer to the decision layer. Yes. You know, GANs, from the previous slides, you can tell that GANs have actually significant flexibility for use in detection of these attacks. There's the discriminator that you can threshold the probability of real produced by the discriminator to make detections, or you can also use this reconstruction loss as a detection statistic. Moreover, the GANs also produces a class posterior. So the GANs itself can be used for making class decisions. We're not reporting results for that here, but in fact, the classification results produced by the GANs discriminators class posterior rival the performance of the deep neural network classifier itself. So the GAN seems effective as a detector and also, in fact, potentially as a classifier. Yeah, I don't know if we, in the interest of time, I don't know if we want to talk about adversarial robust.
This was covered in an earlier talk, actually. This is the part I said we could maybe skip over.
David, I think we actually do need to wrap up here. Do you have a last slide that we can jump to?
I mean, effectively in previous talks, people have talked about backdoors, so that we don't have to talk about it here, Trojans. And just to wrap it up, our references are on this webpage. or on the archive.
Yeah.
Thank
Yeah,
you, David.
And we have substantial work actually on detecting backdoors.
Yeah. Okay.
Lots of it. Yeah.
This is super.